Okay, so anyone else have anything to share, comments, questions? We jump into stuff. Anything new? How are things going with your students? I've heard from my TAs, but the rest of you. I'll assume everything.
Can you hear me?
Yes, Gloria.
We're getting a late start with 2 of my students, and the other one is actually doing some interesting things. He's going to combine the Skynet laboratories with a Coursera course from Rutgers on data analysis and processing for astronomy. So I'm kind of looking forward to seeing what both of these groups do.
That's interesting. So is this student going to be using Skynet as a tool to help with the Coursera course? Or
he's gonna work through the labs as they are in Skynet. And the Coursera course looks at a different image processing system, and it does a few other different, and I'll send you the link to that one that he's taking, because it's kind of interesting.
Okay, yeah.
And the reason I'm
go ahead.
The reason I'm doing that is because he already has an undergraduate degree in chemistry, and he wanted to know about follow-on astronomy courses. And my school, we only have me teaching an intro astronomy course. So I pointed him to the professor at Rutgers. That's the closest.
That's good. And if they're doing data analysis, they're of course using some other tool. It'd be interesting to hear the feedback from the student, comparing and contrasting the analysis activities they did in Afterglow versus whatever this course is using.
Yes.
Some things we do better and some things we do worse. And I'm particularly interested, well, in both, but particularly interested in the things that we might be doing worse so we can improve them.
The Rutgers Coursera course uses D as in Douglas, S9.
Oh, yeah. Okay.
And the student is also using Micro Observatory and JS9. So he's using all 3.
Okay. Yeah, the things that we're going to be doing worse at the moment, like we don't do color combination, and there's a lot of that in DS9, but that's being added as I showed you last week. That's also the reason that the dev version hasn't been pushed. It's still on the Sparge link. So those of you who have gotten up to Lab 5, this is like the biggest bug that we've encountered, the most common, the one that students encounter the most. And that is, it works fine in Chrome, but in other browsers, the photometry tool isn't working. And that's fixed in the dev version on Sparge. So if they're using Chrome, they can keep using what they're using, but if they're not, you may want to send them to Sparge. And there are other things that have been updated. The interface is a little bit different, but in small enough ways, they should be able to figure it out intuitively. But my team is building color combination in to there first, and then they'll push it to the main server. All right. Anything else?
I've been working with Cengage this week to do Moodle integration of the course for next semester, and that's surprisingly easy.
Okay.
So just a bit of feedback on that. Yeah, it's been really, really simple, which is wonderful. So anybody who's integrating to Moodle, it's a few clicks and done.
See, when you first asked this question, I remember you asked it early in the semester, and I didn't know that you could do integration to these, what are they called, digital learning platforms? Is that the proper term?
LMS is Learning Management Systems.
Okay, LMS, yep. And I didn't know they even had an integration. And I think my answer at the time was it's just like a separate textbook and you just deal with it. But the integration is for like gradebook stuff?
So the gradebook stuff is not there yet. Apparently that's in process. And it does, so how to integrate it into Moodle at this point is basically you have easy links to go to specific places. So it does take you to a different place. Like it's not completely integrated, and that like you can't open, say, our version of Moodle As You Learn, and it's right there on the As You Learn page. But
Okay.
it's very simple. It's not like you have to, it's not complicated for the
Okay.
students, because I'm finding that, you know, with the cognitive load that's going on right now, our students are a bit less, if they come across a barrier, they're a bit less able to deal with that barrier, and I get an email instead.
Mm-hmm.
So we're trying to make it as simple as possible, and it seems like it will be much more seamless than having to go to a separate, well, you still have to go to a separate site, but it's an easily done thing rather than they have to remember to log in here and then they have to remember to log in there and so on.
And once it's done, if you could shoot like a screencast and just show me some of the features, I'd like to see that, because we don't use Moodle. I've never seen these integrations before, so that would be good for my own learning, understanding.
Okay. Yeah, I'm meeting again with them next week or the week after. And so that'll be more done. So once that's the case, I will show you what we got.
Yeah, yeah, and no rush on that. My brain is full. My body is tired. You know, we're just
Aren't we all?
Yeah, I know exactly. When you said when the students are confronted with the new digital learning challenge, they tend to fall off easily, and I think that's true for us too at this point. Okay, so
Absolutely.
yeah, yeah, and kudos to all of you for continuing to show up at these meetings, particularly given that I know we're all overwhelmed, and so I appreciate that you're still engaged in this. I like it. Okay, so I have a handful of announcements. Let me go through them. The first is, let's say I am screen sharing. So here's Skynet Live, and here are the Chilean prompt telescopes. We're back. So very happy about this after 7 months of being down. I mean, it's great for you all as educators. You have access to our best telescopes again. It's particularly good for me, for my group, because some of these telescopes we sell time on, and we've been collecting people's money. And so I'm not in a position to do refunds. The observatory is not in a position to refund the money I pay them. So it's just it was becoming uncomfortable. And so I'm very glad to have these back. I've been trying to make it up to them by giving them access to other scopes and whatnot, but they're back for you as well. And I've added some of them into the student's time account. So the time account the students have, at the beginning of the semester, I removed all the telescopes that were COVID closed, but now I've added some of these back in. Not prompt 1, because that we don't actually have any time on that one. I had to, part of the deal, they wanted, I normally keep 10% of each telescope, and I didn't add prompt 2 back in. It has kind of a pretty picture camera on at the moment. It was being used by astrophotographers. It requires much longer exposure times, but we're gonna switch that out and put a scientific camera on it next time we can go to Chile. But I gave you all access to prompt 3, prompt 5, and prompt 6, and that should be plenty to meet the students' needs. Okay, so that's that. One issue that's come up, Stan Converse brought this up. He can't meet at this time, but he emailed me. He's doing lab 3 right now. It says, my internet connection is unstable. You all have me still? Okay. Sorry, just got a warning there. For lab 3, over the summer in the sample directory, I put a data set that they can use, just because we were really low on telescopes over the summer, and some students were having problems getting enough data to do the lab. So I put that in there, and I left it in there this time, this semester, just in case you all needed it. Well, actually, because I forgot it was there, but maybe it was useful. But it can also be problematic. Stan said a lot of his students are just not doing the observation and just grabbing the sample data. So my plan was to remove it and actually go through the sample directories and remove anything that's not needed, particularly now that the CTIO telescopes are back. And is everyone good with that? Or if you're in the middle of lab 3, you may not want me to change it midstream. Are there any preferences? Okay, so.
Oh, actually, I'd like to have it available just in case. Maybe so that if I got a student who's really in trouble, I can kind of just one-on-one tell them about the existence of this.
Okay, yep. And also, we're going to talk just a little bit about some measures that we're taking and thinking about taking for cheating. If you have your own observation, like if you collect this data yourself and have it in your directory, then there'd be an option for you to share. Or right now, the group folder is available to all students, so you can tell them where to go in the group directory to get data as well. Or I can also move this out of the Astro 101 and put it in some place that you wouldn't expect, like Supernova Search or Skynet Junior Scholars, and some obscure subdirectory, and then let you know where it's at. Maybe that's the approach I'll take. Let me make a note about that. Okay. All right, so we've been thinking a little bit about, and this kind of gets us into the issue of students sharing data. And for some courses that you can imagine doing with Skynet, some more advanced activities, student sharing might be encouraged. Like if we had gotten the funding to do the multi-wavelength universe curriculum at the same time, we would have had like one student collect R-band data, one student collect V-band data, and so forth, make color images that work in teams often to do kind of next level activities. So sometimes sharing is good, but sometimes sharing is bad. Like in this lab, we kind of want the students to collect the data themselves. That's what the preliminary education research shows, that collecting your own data and that data image ownership, and I did this myself, it's a big part of why this is successful, at least from an attitudes point of view. Some students, maybe they just forgot to put in, particularly if it's like a repeating sequence that takes a week or so and they wait too long, then they're kind of in trouble. But some students are just being lazy about it, knowing that they can either grab data from the sample directory, as we just talked about, or they can go into the group directory. So if I go here and go to Skynet, let me try again. Strange. Let me refresh the page. Yeah, there we go. Go into Skynet. We have user, group, and collaboration. And some of them are beginning to figure out they can go in the group observations and grab somebody else's data, or the collaboration, which includes all groups doing this lab. So the data is there. And that's not really the goal. So what we're planning on doing is, first of all, removing the collaboration level. It's just too huge and bulky. And the group observation will only be a student could, in theory, be members of multiple groups. Usually it's just one group, but it could be multiple groups in theory. And we're going to put a switch in Skynet where group administrators can choose whether that directory is shareable or not. So for this curriculum, OPIS, we'll probably start with the default of it not being shared. So they don't have access to everyone else's data. Because none of the activities in this lab are built around, okay, you're going to work as a team, you collect this, you collect that. Now for labs 4 and 5, the instructor is collecting data because lab 4, that's the parallax observation, requires that target of opportunity level. In lab 5, it's the RLIRE, which requires a lot of observing time, more than we want to give to each individual student. So the idea is you could turn group sharing on for labs 4 and 5 and then turn it off. And that's kind of like iteration 1. And we'll do something more intricate. We're rebuilding Skynet, the back end and the front end. So over the next year, a lot of things are going to change, and we'll probably develop a more intricate interface where you can choose to share individual observations and things like that. But right now, we're just going to give you an on-off switch. So that's that. I probably no problems with that. That's probably something that'd be helpful to you. Something else that's come up, well, something again related, is another way to check and see if the observations actually belong to that student, if the analysis was even done by that student. You can imagine a student's in Afterglow, and maybe they're using their own data, maybe they're using someone else's data, because Afterglow is soon going to support uploading your own images. So you can imagine someone downloads a FITS file, emails it to the other student, and they upload it. So even if we make the group directory hidden when we want it to be, they could cheat in that way. So Stan has requested some way to check, who took this data, what is the observation ID, and who did the analysis in Afterglow. So we thought about it. We don't want to add more boxes and things for students to fill in WebAssign. So we're going to try to attach this data to the images. And I did a little test in WebAssign. Here I am grading Lab 5, and I uploaded just a picture that was on my desktop, a picture of a painting, just because I know there's information there. Like the astronomical images in Skynet, currently there's very little in the header. But then what I did is you can do a plugin into your browser. It's called an EXIF viewer, EXIF. They're free plugins. I grabbed the one for Chrome just to do some testing. And then once you do that, you can right click on any image and show the EXIF data. And here you can see all the information that's attached to the image. So we're going to figure out how to take the FITS header and put that into the EXIF information in the saved JPEG. And among those pieces of information will be what's the observation ID, who took the observation, and who's logged into Afterglow saving this. And so with just one click, once you bring the image up, and actually they even put a little thing here for some of them, one click, hopefully you'll be able to find that information very quickly to check for student cheating. So that's the other idea that came up. All right. Then my only other announcement, does anyone else have any thoughts or ideas on cheating mitigation? Okay. I mean, it's always an issue, not just with us, but with like any laboratory scenario. So we're beginning to think about that. Our focus was on getting the new version of Afterglow working and getting the labs updated, but we want to take this seriously as well. Okay, before we get into Lab 7, Lab 8 is the last lab. It's coming up next week, and it's not a Skynet-based lab. It is Hubble's Law, and I like this lab a lot, where we use rubber bands and can reproduce the expansion of the universe and why it looks the same for every galaxy and accelerating versus decelerating. But you need certain supplies, and a lot of the students are at home, and so they're going to have to round up these supplies themselves. Fortunately, they're fairly easy supplies to come up with. Dylan put together, I'll email this to everyone, but I'll also put it in the chat. Trying to grab the box here. A parts list. This actually has all the parts for Lab 2 and links to find the supplies, the globe version of Lab 2, if you ever want to do that. Here are links for everything except for like string. That should be easy enough to figure out. And for the PVC cages, if you have multiple ones. But for Lab 8, these are the supplies the student will need. Either poster board or cardboard or a bulletin board, something they can push tacks into, or push pins. And scissors, pen, ruler with a centimeter scale. Go ahead, Dylan.
I didn't include the ruler or scissors just because the old one didn't, but do you want me to throw those in there with a link? I can do that right now if you want.
Oh yeah.
Right now I just have.
Yeah, that's great.
Yeah.
I mean, some of this stuff, if we're doing this on campus, we all have rulers and scissors and pens and things, so we don't need to. But for the students, a ruler with a centimeter, all rulers, I think most rulers have centimeter scales, but they may not have a ruler at home. I don't know. But anyway, you may want to give them a heads up. Here at UNC, we scheduled 2 weeks to do this. Since it's manual, we're going to spread them out, only have like 1 or 2 people in the room at a time. So we schedule like 2.5 weeks to run them through it slowly without over densifying the room. But now they're going to do it at home, and we're just going to tell them, hey, start rounding up these supplies. Tricky part is the rubber band. The rubber band has to expand to a certain size. Let's see, it's written in the equipment part of Lab 8. Yeah, it has, once you cut it, it has to be able to expand. No, it has to be 18 centimeters long once cut. So it can't be too small. And once they cut it, it should be about 18 centimeters. Okay, and yeah, and so they'll need to start rounding that stuff up. Okay, enough with announcements. Let's get into Lab 7. Lab 7 is kind of different for a variety of reasons. It, you know, we're at this point where we're at kind of galaxy scales, Milky Way scales, and we're about to go to cosmological scales. In Lab 8, we're going to, you know, as we said, Hubble's law, which is redshift, but it's cosmological redshift. And to really understand cosmological redshift, you first need to understand Doppler redshift. And so that's one of the boxes that we're going to check in this lab, learning Doppler redshift. One of the boxes is spectroscopy. That's a kind of important thing that students should learn. And sorry, 1 second. Hey, I'm teaching right now. Give me a few at the end of this hour. Okay, sorry. So right, boxes here. So before they can do cosmological redshift, they have to learn the Doppler effect and Doppler redshift. So we're going to cover that in this lab. Spectroscopy, that's something that's really good to get in an introductory sequence. And normally you'll do that with, you know, in traditional labs, you may have like an element lamp and they're doing observations of atomic transitions in the optical. And that's usually kind of a little bit boring, right? You're trying to do astronomy and here they're looking at element lamps. So here we're going to do spectroscopic observations. It'll be in the radio, but still spectroscopic observations. And radio, this is another box that we're checking. You know, these are optical labs for the most part, but radio is the other ground-based window. So it's good for them to get some exposure to that, particularly since we have a very large radio telescope integrated into Skynet. Perfect opportunity. Normally you don't do radio because most people don't have access to these telescopes. A small optical telescope like they're using, 16-inch optical telescope, the counterpart for that in the radio is maybe 10, 20, 30 meters across. And most people don't have access to that, but we do through Skynet. So they get a little bit of radio experience. It's also different. This lab is kind of background heavy. And so we'll spend a lot of time going through the background. Now, if you're doing this integrated, 1 second, let me mute you, Gloria. You have some background noise. Okay. If you're doing this integrated in a lecture course where you're covering the whole universe in one semester, or you're teaching Astro 102, a second level astronomy course, you'll cover a lot of these things in the lecture. And so you won't have to focus so much on the background. But if you're doing it standalone, then there's a fair amount of background material, more than most labs. But the trade-off is when it comes time to actually do it, this lab actually goes very quickly. It's easy to execute. So a lot has to go into the front end for them to conceptually understand what they're doing, but then the execution of it's pretty easy. And then the other way this is different is the math level. It does have some trigonometry. And we've tried to keep this for the most part at the high school Algebra 1 level. But in this lab, you do have to have a little bit of trig, but the nice thing is they don't need to understand it deeply. There are a few sign functions, and really they just need, it's clear from the instructions what the sine function does. It takes you from this leg of the triangle to this other leg. But, you know, if they don't know what a sine function is, they just need to be able to press the button on the calculator. So there, in addition to the math, there's some geometry, and sometimes that can be tricky for students as well. Anyway, let's open it up and start looking at it. Okay, so the intro stuff at the top, I still need to shoot the videos for this one and update it. I have all the videos, overview videos shot through lab 6. The goals. So in this lab, we're going to measure the speeds at which material orbits the galaxy. So again, using the Doppler effect, we're then going, after doing a number of these measurements, we're going to build a rotation curve of our galaxy. And by looking at the curve, the students will be able to determine whether, well, how the mass is distributed. Is most of it concentrated at the center, like in the solar system, or is it spread out? And the answer is it's spread out. We know that, but students think the opposite. They know there's a supermassive black hole at the center of the galaxy, and they think that's the majority of the mass, and that's not the case. It's a minuscule amount of the mass. And then the third part here is we're going to measure the mass. By looking at the rotation curve, you can figure out the distribution of the mass, but we're going to actually measure it out to different radii, the contained mass within different radii, out to our distance from the center. Then we'll throw in a few extra points that they don't measure. Basically, this technique in this lab works out to our distance from the center, 8 kiloparsecs. So we'll throw in the 2 Magellanic Clouds also, where they won't do the measurement, but we'll provide the speed and the radius. So they can extend the curve a little bit and then contemplate dark matter. So this touches on dark matter just a little bit. The next lab touches on dark energy just a little bit. They're kind of like the carrots. And I guess the instructions are the sticks, but the interesting topic of dark energy and dark matter, those are carrots. Okay, equipment, just the internet connection. You can see we got 1, 2, 3, 4, 5 different background sections here. I'll go through them kind of quickly because we spent a lot of time talking about other stuff. This is all stuff you know, but I'll give it a quick presentation as if you were students. So the Doppler effect, and I like using slides like this to explain what the Doppler effect is. Here we have a stationary source. These blue circles correspond to crests of the waves coming out from it, or troughs, or any common position in the waveform, and maybe view them as the crests. And so the observers, whether on this side or that side, will observe the same wavelength as is emitted. But if the source is moving, or equivalently, if the observers are moving relative to the source, but it's easier to think of it this way. Here, the source is moving. Each of these circles is centered on the emission point. So here's circle 1. It's centered on where the source was when it was emitted. Then it moved over here and emitted from position 2. So that circle is now out to here. Position 3, it's out to here, and so forth. And so the crests get compressed in the direction of motion and spread out opposite that. So the wavelength that's observed is the emitted wavelength minus delta wavelength, or plus delta wavelength, minus if you're moving towards each other, plus if you're moving away. And the delta wavelength is given by the Doppler effect equation, which is right here. It's your emitted wavelength times your change in velocity along that line of sight divided by the wave speed, which is the speed of light. And that's something we have to emphasize. Your component, it's your component of the motion along the line of sight. Often when these Doppler shift problems are presented in class, you give them simplified examples where something's moving directly towards you or directly away. In this lab, we're going to have motion with a component of it towards you or away. So you do have to make that distinction. Okay, then this next section is on the 21 centimeter emission line. We start with an optical picture of the Milky Way, and you can see the dust lanes. So there's a lot of dust. If we want to figure out how the galaxy is rotating, we need to be able to observe it, and the dust is blocking us at optical wavelengths. even the light you see is kind of nearby. The deeper you go into the distribution, the more of it is blocked by dust. So we need something that can penetrate the dust. Dust gets up to about a micron in size. And so as long as you use wavelengths that are larger than that, you can penetrate the dust. That means you have to go into the infrared or longer, and get a little bit too far into the infrared, you have to go into space, but we have the radio window at very long wavelengths. So that's the idea. We're going to go to the radio so we can get through the dust. We just need a line to work with, an emission line. And we have one. We have the 21 centimeter emission line. And it's a little different from any emission line that they're used to. They're used to atomic transitions. They've learned that if the electron hops from this level down to this level, you get a photon. And that will be at a visible or infrared or ultraviolet wavelength. This, to get something at a radio wavelength, very low energy, it's a much more subtle effect. It's not due to a transition from level to level. It all happens in the ground state. So here's hydrogen, the simplest atom. When you explain it, maybe bring 2 bar magnets to class. You have the proton, you have the electron, they're charges, they're spinning, so they're little magnets. And just playing with bar magnets, we know there's a configuration where it's easy to put them together and a configuration where you have to apply a lot of energy to hold them together. So there's a slight energy difference depending on which way the electron is oriented. So you have hydrogen out there in space in these giant clouds. It gets jostled. So collisional excitation, it just bumps into something and energy is transferred and it can push the electron into that higher state, still in the ground state, but that higher energy configuration. And then it has a half-life of 11 million years, and it decays naturally back down to the lower energy state, releasing that teeny tiny amount of energy, which corresponds to a 21 centimeter photon. And 11 million years, that's a super long half-life. You may think we won't get much of this, but there's so much hydrogen in the universe that it's a whopping powerful signal. And the spectra that we take, we can do it in a fraction. If the equipment would allow us, we could do it in a fraction of a second and get enough signal to noise. So it's just a very, very strong signal. And so here's a map of the sky in galactic coordinates. It's a map of H1, H Roman numeral 1, which is this 21 centimeter line. And it's cold hydrogen. If it was hot hydrogen, it wouldn't be in the ground state and you don't get this. But cold hydrogen, you see it's very concentrated in the plane of the galaxy. And of course, that's where stars form, and that's out of what stars form. Okay, so let's start building up the rotation curve. We know we're going to use the Doppler effect. We know what line we're going to focus on. So how can we start building up the rotation curve? Well, we're going to point our telescope at various locations along the plane of the galaxy, starting at the Galactic Center and moving off in one direction. In the Galactic Center, we shouldn't expect a redshift or a blue shift. So here's kind of a top-down schematic of our galaxy. And how do we know this is what our galaxy looks like? Well, we can't launch a spacecraft and get far enough away to take this picture. We know it by doing the exact kind of measurements the students are about to do. Radio spectra, penetrating through, getting hydrogen or other radio lines from each of these arms and then reconstructing it. So they're going to do kind of a simple version of this, but you can do it in much more detail and figure out where the arms are. And then they hired some artists to spiff it up a little bit. And probably the accuracy of these kinds of top-down maps are 10, 15%. It's probably not exactly right, but it's pretty close. And so we use these, just try to get to convey the concept of what they're going to be observing. So here's the sun in the outskirts. In the previous lab, we learned that we live in the outskirts. We're 8 kiloparsecs away. So again, we're going to build off that information. And if we're taking a spectrum along this line of sight pointed at the center of the galaxy, I've drawn a little red line here wherever we cross an arm of the galaxy. And assuming this stuff orbits in a circular fashion, that's a geometric assumption that's made in this kind of analysis, then nothing is moving towards us or away from us. There's no component towards us or away from us. So this should just produce the hydrogen line, not redshifted or blue shifted. And when you take this spectrum, it comes out looking like this. And so there's, in a perfect world, there'd be nothing here except one big broad bump. But looking at the Galactic Center, it's a bit of a technicality because we're not just looking at all this hydrogen along this line of sight. There's also a bright radio object there at the center of the galaxy, Sagittarius A star. And some of that emission from the source emission gets absorbed by hydrogen along the line of sight. So what we have is a broad emission line, but we also have absorption right at the same wavelength. And there's another absorption line over here. This would be material that's moving, let's see, it is moving towards us, I believe. Yeah, it's blue shifted. So when they get this, it does require a little bit of interpretation. And so I've thrown this one in the lab, and also in one of the videos, I spent a lot of time explaining what they're looking at. But you kind of have to mentally fill in the gap, and this is the emission line here. Okay, now if you were to look over at the side at a different galactic longitude, and they learned the galactic longitude system in the previous lab, it's something like this here. So you're going through and you're penetrating the arms at different places, but there's one special place where the motion of the material is completely along the line of sight. And that's where you're going to get the biggest redshift. I'm cheating a little bit here by drawing these arrows all the same length. It's kind of assuming a flat rotation curve, which is what they're going to find, but just pedagogically to explain the angles and how that will work. I kind of gloss over that here. But you know, for each point here, I've drawn the arrow in the direction of motion of that blob of material in that arm. But this is a special point where you get maximum redshift. And it's special because you can draw a right triangle. So the students will be collecting spectra, a dozen spectra, each of them, and they're short exposures, so they'll be able to do it quickly, and each one will be able to collect their own data set. And they'll come back looking something like this, and I'll show you how they'll graph it up. And they're going to be looking for the most redshifted peak. It's not necessarily the brightest peak. Sometimes it is, sometimes it's not. And they'll then need to measure the position, the wavelength of it, to 4 decimal places. So it's, you know, really precise measurement there, but we have the precision that can measure it. Now, there's some uncertainty here. Where exactly is the peak? It's not always clear. Do I measure the peak? Do I measure it right here? Do I measure it halfway up? As long as they're consistent, that's fine. The auto grader is fairly generous. So this is how they're going to measure the motions of individual blobs. Yeah, radio spectra. They're going to collect their spectra. They're going to find the most redshifted point, measure that wavelength. Okay, now to build a rotation curve, we need 2 things. We need how fast is this blob moving, and how far is it from the center of the galaxy. We'll do that for a number of points, and then you figure out how fast everything is rotating around the center of the galaxy as a function of its distance from the center. So for this special point here, first, the radial distance, it's really simple. This is the galactic longitude, this angle from the center of the galaxy. We know our distance from the center from the previous lab, 8.1 kiloparsecs. And so the distance of the special point is 8.1 times sine of that angle. Again, there's the trigonometry. And they can see it here on the figure, even if they don't know what a sine function is, they now understand that's how I'm going to get this leg of the triangle. So that's pretty simple. The speed that it's moving is 2 steps. It's a little bit more complicated. They use the Doppler equation to figure out the relative speed between, you know, how fast it's moving compared to us, because we're also moving, and so we'll have a component in that direction. So the Doppler part of it right here, basically they're going to measure the change in wavelength, divide by the emitted wavelength, multiplied by the speed of light, and they get the delta V part. And, you know, here's another example, again, emphasizing it's not always the highest peak. That's a common mistake students make, but the most redshifted peak. So they're going to get that and calculate the delta V, but then they have to add that to our motion along that line. So we're moving at 220 kilometers per second. This comes from looking at galaxies all around us and figuring out our motion relative to kind of a standard of rest. And then our component along this line of sight is 220 sine L. So they have the Doppler component and they add 220 sine L. Then they have the velocity. So then they have 12 velocity radii combinations, and they can plot up a rotation curve. And we'll do that down in the procedure. Here's the last background section. Again, I said there's a lot of background here. And this is converting it into a mass. And we start with this idea. Here's Earth going around the sun, and our orbit's pretty close to a circle. If the sun's mass were to drop to 0, we wouldn't be on a circle. We'd just fly off in whatever direction we were heading. Or if the sun's mass were to increase tremendously, we would deviate from a circle and move inwards towards the sun. So clearly, if we're in a circular orbit, it tells us something about the central mass, how much mass has to be there to keep our orbit the way that it is. And Newton showed that it just depends on the enclosed mass. In the galaxy, there's going to be mass enclosed within your orbit and mass outside. All that mass outside cancels out, which is a beautiful simplification. And the interior mass is just given by v squared times r divided by g. And they just measured v's and r's. So they can calculate enclosed mass at the same time. Here it is solved for v. And for the case of the sun, for the case of the solar system. In the solar system, all the mass is concentrated at the very center. And so enclosed mass is a constant. It's the same for all distances. And so it goes as 1 over the square root of r, and you get a curve like this. And we call this a Keplerian rotation curve. So if you see, when you plot up the velocity, the rotation curve, if it's dropping off like this, it means the mass distribution is centrally concentrated, like in the solar system. But in general, it's given by this. You have to put in the mass enclosed within that radius. And in galaxies, if you go twice as far out, you enclose about twice as much mass. 3 times far out, 3 times the mass. It's pretty close to linear, which means it will cancel with this r, leaving you just with a constant. And that's what you see. Once you get far enough out, you have what we call a flat rotation curve in our Milky Way and most galaxies. Okay, that's all the background. So how do we assemble this into the procedure? First, they have to collect their observations. And this is new. Before, for all the years prior to this, they were using archival data collected with a smaller radio telescope. But now they're going to collect it with this. A pretty awesome picture of the telescope. It's 6 stories tall, 150 tons. They get to move it around themselves. So there's kind of an oh wow factor. I would love to get a webcam on this, but webcams make radio noise, so it's been very tricky. I'll keep pushing for this because you could put one in a Faraday cage a mile away with a telephoto lens, but it's tricky. Basically, I'll have to do it myself and take it there and then get the permissions. I think that's the way to go. Because I think it'd be fun if they put in the observations, as long as their target's up, this thing usually is available and sitting, and so they'll be able to see it move. And with our new notification system that we're building, even if they have to wait, they'll get a notification, okay, your job is being executed, and they can log on and watch this thing move, at least if it's daytime. And there are links to the observatories, and they can learn more about the telescope. We refurbished this with Stimulus Act money from the previous recession, so there's a link to some of that history. Okay, how to put in these observations. There's some reminders here, but they're going to put observations in at galactic longitude 0, 8, 16, so forth, all the way up to 88. And I'll just show you quickly how that's done. Go to Skynet. Radio observing. And there's a good video on this that you can watch as well, but I'll just do it real quick. I'm going to add a new observation. You come down here and you switch the coordinates to galactic. And we'll start with 0, 0, which is the Galactic Center. You got to give the file a name. It may help to put the longitude in the name, just making it easy to sort through your files as you save them on your computer. So I'll name this GL0. Sun separation can be 0. We can observe during the day, even close to the sun. Minimum target elevation. The Galactic Center, which I've just selected, well, no, that's the coordinates of it here. But here you see it's pretty low in the sky for West Virginia. So minimum target elevation, if you drop it down to 15, it gives you a longer observing window, more likely to get it. And the ones that are farther from the Galactic Center are higher in the sky. And so it's, there's a longer window to observe it. The observability chart doesn't work in galactic coordinates. It's something we'll fix in the next version. Save and continue. This is the analog of picking your filter. For optical telescopes.
I'm sorry. Can you hear me?
Yes.
I didn't know that that telescope went down to 15. I thought it only went down to 20.
Nope, you can take it all the way down to, I think, 0. But if you go too low, you're starting to observe the mountain range, and it's making a lot of radio noise. But yeah, it does, and we've tested this out. 15 will work fine. Yeah, I think you can bend it all the way over. It's a pretty impressive piece of equipment. Okay, this is the analog of where you're picking your filter. On the optical telescopes, it's a piece of glass. Here it's done all in the electronics. And normally when this comes up, you come to this page, it's in low resolution mode. They're gonna have to switch to high resolution mode to see this line. And this will then automatically fill in 2 frequencies, here and here. It's gonna take 2 high resolution spectra separated by about 15 megahertz. And the second one is centered very close to where we need it to be. So they don't need to modify anything. The numbers come up automatically. They just have to put it in high resolution mode. They can keep the channels at 1024. Save and continue. And there are all sorts of different types of observations. We can do maps, we can do daisies, on-offs, but that's more advanced stuff. It takes more observing credits. Here they're just going to track. And I've updated the lab to say 2 seconds. 1 second was creating some problems, and we're still in negotiations with the observatory of how to handle those problems. Normally it works fine, but their equipment kind of updates on a 1 second scale. So occasionally you get into this weird race condition and it jams up the telescope. And it's okay if it throws an error flag and the queue is held. But this summer it was not throwing an error flag. So all the observations would just pour through and nothing would happen. And the students would have to resubmit. And so we're being, watchful. We're being watchful for that this semester. And we're working to get this debugged with them. Until then, we're going to do a 2 second duration. Hopefully this will resolve the issue. Most of the time it works, even this summer with 1 second, worked just fine. But occasionally we ran into this weird case. So 2 seconds. The video currently says 1 second, but in the title of the video, I put a note in in all caps. And I'll shoot a new video once we know exactly what duration will be error-free. But 2 second duration is plenty of time. Save and continue. Submit. So it's very easy. It's as easy to put these in as the optical observations, very similar in pattern. And then you have to put in the other ones. Instead of retyping everything, just go to the one you submitted and hit resubmit, and it will come up with everything filled in just as you did. So after 0, we're going to do 8 degrees. And then you can just click through everything. Save and continue, save and continue, save and continue, submit.
Change the observation name, eh?
Yes, thank you. You want to change the observation name. Yep, I did that too fast. So I will actually click on this one and cancel it because I didn't do it right. Yeah, change the longitude and the name. Okay, and then once it comes back, maybe I'll grab one of these here. We don't yet have our own page for this, but you can go to Greenbank's page. And there's a lot of stuff here, but all they really need, and this is explained in the video and in the lab, is the calibrated spectrum. So they can right click here, save link as, and it saves it as a text file. Okay, then I'll just click on and show you, it's just a text file with information in there. But they save it onto their computer, and then they go to the graphing tool. Here it is. And you'll go to the spectrum option. And you'll then upload that file. These all begin Skynet. I think this is the one I just saved. What did I load?
I'm sorry, what format did you save the file in?
It's just a text file.
Okay.
Let me see what I loaded here. Oh, yeah, that's a Galactic Longitude 0. file. It's not the one I just saved. I saved Galactic Longitude 16. I can load that one in. Let me find it. Here it is. So that's the one I just saved, but it doesn't matter. You know, you save them and upload them, and they'll be able to measure, like, here's the most redshifted peak. They hover over it and they see 21.1141. There's their measurement to 4 decimal places. If you see nothing here, it means the channel's dead. Occasionally, one of the 2 channels will die. They can just switch over to the other channel. If both channels are dead, you got to let us know. We have to send out a repair team. And then filling in the axis labels and titles that's explained in the lab in the video. I won't do that.
That's really great because I make my students read through all that data to find those peaks.
Okay, this will make it a lot easier. So I won't go through the title stuff. You can figure that out or look at the video because I'm running low on time, but we're almost there because I said the procedure part goes really fast. Okay, so this is where they're putting in their observations. Here they're building the rotation curve. They measure the observed peaks here, and then they're going to calculate the Doppler shift, the sun's component, add them together, and the distance from the center of the galaxy. And there's a tutorial on how to do, well, this is a tutorial on how to make those measurements. And then we have a tutorial on how to do this in a spreadsheet. They can do it all by hand if they want to, but in the previous lab, we taught them, it's over on my other screen. We began teaching them some spreadsheet skills. Well, in lab five, we began teaching them some spreadsheet skills. And so we can continue here. And so we have the spreadsheet ready to go, but the equations are not in there yet. They would have to do the equations. The first is going from degrees to radians, because the sine function in these spreadsheets, they're expecting something in radians. So, you know, it's just equal to this divided by 180 times pi. And once they type in the equation, they drag down and they'll put in their observations here. I'll just enter a few numbers. And they can code the equations. And there's 2 ways they can do it. And I know you know basic Excel here, but I'll just point it out. We have all the constants they'll need over here. So they can just click on the constant. So change in wavelength divided by the emitted wavelength times the speed of light. But if they do it this way, they're going to have to put the exclamation points between the letter and the number for the constants. Sorry, dollar signs. Before they can drag down. Otherwise, they'll be dragging down the logic of the constants. So that's one way they can do it. The other way is they just use this table as reference and enter the constants in by hand. So this would be equal to this minus 21.1061 divided by 21.1061 times 3, 1, 2, 3, 4, 5. So same value, and then they can drag the logic. I lost. Oh, I typed it in here. And they can drag the logic down. There we go. So either way, they either put in the dollar sign or they just use this as reference and type the constants in by hand. This is just 220 sine of L. They'll want to use the L in radians. This is the sum of the 2 velocities. I'm doing it really quick. And this is 8.1 times sine of L. Just need the equal sign. And there's another bit here for the last bit of the lab where they'll do the enclosed mass, and I'll come back to that in a second. But they put their measurements here, they enter the logic, drag it down, and it does all the calculations for them, and they learn a little bit of Excel at the same time. And they can enter those into here. It grades very generously. And then they honor code pledge, sample figure, and an example of each of these calculations. And then they go back to the graphing site and using the most basic option, just the basic curve. They're going to plot velocity versus radius. This is the answer key. They should get something like this. These are measurements I made, and it's clearly a flat rotation curve. So it asks them, is this a Keplerian or a flat curve? It's flat. Does this mean the mass is concentrated near the center or spread throughout the disk? It's throughout the disk. Sources of error, difficulty measuring the wavelength. The most redshifted peak, it's sometimes blurred together and not 100% clear. Other sources of error, the true special point, there may not be an arm of the galaxy there. It may land between two arms of the galaxy. And so they're, again, the closest thing to it. Also, Earth is going around the sun, and that creates a shift as well that we're not accounting for in this lab because it's small. You can actually see it here. When we looked at the center, we had a negative speed instead of 0. That's Earth's motion around the sun. You can, if you want to be more careful, you can model that and build that in, but here we just treat it as a source of error. And then the last part is actually calculating the masses. And again, the equation is just v squared r over g. And we've converted g into the units that they have. They have velocity in kilometers per second, radius in kiloparsecs. And so you can come up with a value for g in those units, and it's 4302. So in the spreadsheet, they then just take the velocity and square it, multiply by the distance from the center, and divide by 4302, which is here in the constant table as well. They can drag that logic down. And as we'll see in just a second lab, we've also thrown in the LMC and the SMC. They're not measuring those through this rotation curve technique, but we give them the speeds and the velocities so they can have 2 points way, way out there beyond the disk as well. So they enter those into this table, show a sample calculation. Here's the bit for the Magellanic Clouds. They enter their enclosed masses there. And then again, using the curve feature on the graphing tool, they graph up their data, and here are the Magellanic Clouds here. This is enclosed mass versus distance. And then we ask them a series of questions to round it out. Using your graph, estimate how much mass is within the sun's radius, which is 8.1. That's that last data point. And somewhere around 70 billion solar masses, gigasolar masses. In lab 6, we measured the diameter of our galaxy to be 34 kiloparsecs, half of that's 17. So go to this chart, go to 17 and estimate it, eyeball how much mass is enclosed within 17. It's about 230. Then go out to 61, the SMC, how much mass is enclosed out there? It's about 900. Then we ask them how much mass is between the edge, the visible edge of our galaxy, 17, and the SMC. And it's the difference of those two, so about 680. We ask them, is there more mass outside the visible part or inside the visible part? And so it's 680 versus 230, so there's more mass on the outside. And then we give them the mass of the LMC and the SMC, and they're minuscule. So what's the question? Is our galaxy mostly visible matter, like stars and gas, or mostly dark matter? It's mostly dark matter. Then we have a box here for them to research and discuss dark matter and what it might be. WIMPs and machos, and basically they can just go online and learn a few things and put it back here. Anyway, I was rushing near the end, but you can see the procedure section goes really quick. Most of it is building up that background, which again, you may be doing as part of your lectures, depending on how your course is set up, but it also works in the standalone format. You just have to do more background here. But then execution is pretty straightforward, particularly if they're using the spreadsheets. Okay, I'll stop. Questions, comments, feedback? It's different. You know, I don't think in any introductory lab course, well, you don't usually have this lab, right? Because they usually don't have access to these kinds of radio telescopes. Sometimes you may see it in a more advanced course, but usually there the data is given. But here we brought it down to the introductory level. And I think it sets you up nicely for the next lab. And also, we did a publication on this. Catherine Williamson did this lab using the 20 meter before we even coded it up to use the 20 meter, and got some really positive results with it. And there's a publication in our TSRE led by her. And we built some of these tools in response to what she was doing. And she figured out how to do it with the 20 meter, but she didn't have these graphing tools like Gloria said here. So now you have those tools. Okay, I've gone about 5 minutes over. So thanks. And next time we'll take a look at the rubber band Hubble's Law Lab. And we'll also discuss the post surveys that we're gonna have to do. And I'm going to set up a Google Doc for you to start giving me feedback divided into the various labs. And so you can put comments there for me to add things, improve things. That's the point of doing all this. This semester is more about ramping up learning the material. But as you go through it, you're probably learning, hey, it'd be great if we had this or if we didn't have that. And so we need to start getting that feedback in an organized fashion. Okay. I'll see y'all later, but I'll stick around if anyone wants to talk.
Thanks, Dan.
Thanks,
This is
Dan.
very excellent.
Thanks, Dan.
My pleasure.
Yep, thanks.
Thank you.
Dan, I do have a quick question.
Yes.
Yeah, so this is really nice, very, very well done. And I've enjoyed every single one of these labs. What is your experience from the students? Are all of your students able to handle them, or is it only the top 20% or top 30% who can do everything, or how does it work?
Our students, I mean, we of course have a grade distribution, and some students fail, but most students do just fine. It's not like there's a peak at the top and then everyone else is at the bottom. It's a nice Gaussian.
Mm-hmm.
And so it's a normal distribution. It may not, with these labs, we've never tried to tune them such that 90% is an A, 80% is a B, 70% is a C. We haven't tried to set the points and the difficulty level to achieve that, which is sometimes a student expectation. But they pretty quickly get used to, okay, I'll get a score and the instructor will convert that to a grade. But those issues aside, most people get most of the points.
Okay, right. So, and this is a non-honors class, right?
This is survey level. 1 in 5 undergrads at UNC do this. Though, now UNC is what the number 5 public in the country. So we do have really good students.
Sure, yeah.
And it varies.
But they're non-science majors, correct?
Non-science majors. I mean, there's some in there that will become science majors. And this lab has actually convinced some of them to become astro majors, which is nice.
Very good, yeah.
But I should say, this hasn't always worked at some of the small institutions. You're not a small institution, but some of the small institutions, usually it's with a professor who wasn't really, I'm still recording, I should stop recording, but the professor may not have been very good, may not have really understood the astronomy. They're not an astronomer, they're charged. It's a smaller, but we also do this at the community college level quite successfully. So it can work all the way down at that level. So the cases where it didn't work, I think it's often more instructor inexperience.
I see. Okay. And so going back to the grading, you said, is it graded like based on, how do you grade the labs?
Yeah, and so I'll show you, I'll answer the question, but I'll also say, I think this was probably before you started joining. If you go to the YouTube place where I'm storing all these, I have an older video. It's a 20-minute video that walks you through how to do grading in WebAssign, the technicals of it. But I'll just show you some of the basics now, and then you can consult that video for more. So let me go to one of my labs here, 412. And let me look at all. Okay, I'll go to lab 1 scores. And it's under here, grade answers. And this one is in 2 parts. And the first part doesn't have anything to grade. So I'm just going to go straight to the second part.
Mhm.
First part is background section. So less things to look at. Okay, and it's loading up, and this loaded up my first student, and you can go to any student in the class here, or you can run through it and then hit next student and then run through that and hit next student. And as much as possible is auto-graded. The parts that are not, we have a Google Doc that's a grading guide, and it tells you, okay, you're gonna have to go and grade this figure and this short answer manually, and gives you tips and pointers. And I'll pull that up in a second. But hopping through this here, I'll just kind of show you how it works. Let's see, this is they did a picture of Mars. There it is. And soon, as we were talking about today, you'll be able to right click, show the XF data, and in here you'll have information about who took it, who analyzed it, so you can check for cheating really quickly. I don't think cheating is rampant, but some people want to check for that stuff, and we want to make it easy.
Sure.
And then it's kind of, the answer key mode is kind of messy, but what we have here is what they submitted, and it gives them full credit automatically. And you can go back and say, no, that one's only worth a 1 because they forgot to zoom in, or there's nothing in the image, or they uploaded a picture of their dog, or whatever. And there's also a space that you can give a comment if you want to. When I'm grading, I don't do comments because I'm so busy, but my TAs, they're supposed to be more thorough, and so they explain and give hints here. And so images that they've uploaded, you have to grade that manually. Also short answers. And so in this part of the lab, they're asked to describe their images. And I have an answer key here, and you can read what they wrote here and give them a certain number of points. And again, the spreadsheet that I'll point you to gives you tips on give points for this, don't give points for that, things of that nature. You don't have to follow those, it's just a guide. And then there are many things that are auto-graded. Whenever something can be auto-graded, it's auto-graded. Normally tables, calculations, where their numerical inputs are auto-graded. Sometimes we have a few special cases where we can't do it fully, like here in lab 1 is one of those special cases because we don't know which objects are observable. And so we have the table here, and the stuff in the table is worth 0 points, but it will auto-grade it. Like over here, they're measuring the angular diameter, and it tells you which ones they got correct. But then you'll have to go through, and it's, here I would give 100%. So this table is worth 10 points. So these honor code pledges that we stick in here, it's really just a place for you to put points. You see, they could cheat by, suppose only Venus, Mars, and Ceres was observable, but they could enter stuff for all the others and fool the auto-grader and get points. So you can just ignore that because okay, this semester Venus, Saturn, Uranus, Neptune were not observable. So I'm just going to look at the checks up here. Did they get all the checks up here? 10 points. Did they get half of them? 5 points. That kind of thing. So we have a few special cases where you have to look at what was auto-graded and then assign the score. But most of the things, like these calculations here, can be fully auto-graded. There are other places where they do sample calculations, and again, you'll have to manually look at those. And most of the manual effort is in labs 1 and 2, and then the farther along you go in the lab sequence, it turns out more and more of it is auto-graded. And you're just basically looking at their graph, seeing if they did the labels and title correctly. You're looking at their sources of error to see how horrendously they butchered that, because students always butcher sources of error. But the grading gets easier as you go.
So typically for a TA, how long does it take to grade one of these?
One of these, the first one will take longer, but once you've gotten a few under your belt, you could probably run through each one in about 5 minutes.
I see.
Again, it's more time for the early ones and less time for the later ones.
Right. Because I'm hoping that I can start using this in the spring, but maybe just the first 2 or 3 labs. But I do want to make sure the TAs can handle the grading.
Right.
So yeah, I'm not going to try this out on our big class yet. Next semester, again, I'm doing the smaller class.
Sure.
In the fall, next fall, I may be doing the big class. But
Okay.
I think the small class would be a good thing to start to check it on.
Yep.
To
And
at
of
least
course,
get used to it.
using just the first 2 or 3, those are the ones with the heaviest grading load. But I mean, that's,
Yeah.
it is what it
So
is.
for those, it would
Yeah.
be more than 5 minutes, like 10, 15 minutes per lab. Or...
Probably somewhere between 5 and 10 once they get good at them.
Okay. Even for those initial labs, I see.
Now, you know, if they want to spend the time and do a lot of comments and feedback to the student, that will slow them down.
Mm-hmm.
Basically, each of my TAs, we have 30 students per section, and they're in charge of 1 or 2 sections.
Okay, yeah.
So they're grading 30 to 60, depending on their TA load.
Right.
And
yeah, I think we have more sections and fewer students per section, but it's the same thing. Yeah. Sounds good. All right, Dan. Thank you very much.
Sure, my pleasure.
Okay, have a good weekend.
You too. Gloria, do you have anything else? Okay. All right, that's it.